Good evening, everyone. Today, welcome to the second session of NPTEL. I am Umar Rashid. I work in Indian Institute of Science, Bangalore, as a PhD student. So, I'll be helping you with some of the sample problems, and I will, in order to explain or try to solve those sample problems, will be going through some of the fundamentals that will help us to solve those problems. So the previous session we have solved some problems from the last year assignments. That was mostly regarding the basics of the thermodynamics. Today we'll be going forward with that, and let us start. So the first sample problem that we have here is the question states that a gas which is initially at 23 degrees Celsius and 1 atmosphere is compressed adiabatically to 1.5 atmosphere. The final temperature of the gas is found to be 37 degrees Celsius. The Joule-Thomson coefficient of a gas will be. So here we have to determine the Joule-Thomson coefficient of the gas. Now, in order to solve this question, we should first know what is the Joule-Thomson effect. So the Joule-Thomson effect is that once a gas is actually at a very high pressure, so the Joule-Thomson effect. So here in Joule-Thomson effect, once a gas, now this is only possible in case of real gases, because the Joule-Thomson effect will be shown by the gas that have molecular interactions. So what the Joule-Thomson effect states that when we have a gas that's under a very high pressure, like in a pipe or in a chamber, and then we that gas is actually going from a high pressure, that is P1, to a low pressure chamber, that is, if we can say, P2. Okay, so if the gas is going from low pressure, high pressure, to that of the low pressure through this orifice, if we say, then what will happen is that if the temperature of the gas here is T1 and if the temperature of the gas here is T2, if P1 is actually less than P2, sorry, if P1 is greater than P2, that means the gas is going from high pressure to the low pressure, then what will happen is that the temperature of the gas actually decreases. So the T2 will be actually, sorry, less than from that of the T2. Now this is the property of the real gases only, because why this happens is that since if we have a gas, like we have various gaseous atoms, okay, so at higher pressure, so if we have a gas that's under high pressure, so what will happen is that there will be intermolecular interactions between any gas particles which is present at very low pressure, okay, P1. Now what will happen is that when that gas is actually transferred to a chamber where the gas particles are far from another, so there will be some interactions that are not present there, or the interactions will be weak, like if we write as V2 and this as V1. Now because of those interactions, the interactions are weaker here, or there are less interactions that are here, so some energy has to be given from the gas. Since we are not giving any energy from the outside, this is in a adiabatic chamber, okay, so since this is an adiabatic process, so what will happen is that the temperature of this gas will decrease, because it will need that and some energy in order to overcome those intermolecular interactions. That energy is actually taken from the environment, and as a result the temperature drops. Now we can prove that this Joule-Thomson effect is actually an isoenthalpic process. So we can say that it is an enthalpic process. That means the enthalpy of the gases which is present at H1 and the enthalpy of the gas actually remains constant. H1 is equivalent to H2. So this is the Joule-Thomson effect. Okay, now practically how we determine the Joule-Thomson coefficient is this. For example, so we take a gas that is coming through this pipe, and it's at very high pressure, and everywhere there is an insulation. And then what this gas is allowed to pass through this porous material, where it goes from a high pressure to that of the low pressure. Now because of that, there will be a decrease in the temperature. Now that decrease in the temperature will be reflected in the temperature of this chamber. Now in order to determine the temperature change between these two, is we use the thermocouples that are actually shown here. These are the thermocouples 1 and 2. So these thermocouples will actually measure the temperature difference between this and this. Now we know that what will be the temperature difference between here. For example, it is T2, and the temperature difference C is here is T1. Now we know the temperature difference. That means delta T has to be equivalent to T2 minus T1. Now since we know the temperature difference between these two, and I know what is the pressure that we have given, that is P1, and this is P2. Now we know delta P, P2 minus P1. From that process we can actually determine the Joule-Thomson coefficient, that is given by change in the temperature per unit change in the pressure as an isoenthalpic process. Now this is actually given if we plot change in the temperature, that means T as a function of pressure, and this slope will be given by mu. Okay, so okay, so now now this Joule-Thomson coefficient, it is being extensively used for liquefaction of the gases. For example, since if we have to liquefy any gases, so what we need to do is we need to decrease the temperature very low. So in order to decrease the temperature, what we'll do is we'll take multiple chambers, like so multiple steps of the this Joule-Thomson effect is happening. So if here it is P1, this is P2, this is P3, this is P4, this is P5, this is P6. Now what will happen is that the liquefaction will happen like this way. So at each temperature, if this is a temperature T1, this will be temperature T2, this will be temperature T3, this will be temperature T4. Now what will happen is that at every process, at every step, the temperature will get decreased. As a result, this T4 is very low as compared to that of the melting point of the gas, and it gets liquefied. So this process is sometimes called as Lewis liquefaction process. Okay, so let us go back to the question, that when the gas was initially at 25 degrees Celsius and at 1 atmosphere, and it is compressed adiabatically to 1.5 atmosphere, the final temperature of the gas is found to be 37. So we have to determine the Joule-Thomson coefficient. Now we will determine the Joule-Thomson coefficient. So we have a sample problem. Okay, so in order to determine that, we know that mu is joules Thomson coefficient. Okay, now is this mu is given by, as we have seen previously, delta T by delta P at isoenthalpic process. Now that is almost equivalent to delta T by delta P. Now we see that how much is the change in the temperature. The initial temperature was kept 73 degrees Celsius, and the final temperature was kept to be 23 degrees Celsius. And how much was the pressure that has been dropped? 1.5 to 1 atmosphere. Okay, so from this process we can determine that mu is 28.28 degrees Celsius per atmosphere. Okay, so this is the answer of the question. Now we have okay, now we have another problem. So this problem states that a chemical reaction takes place in a container at 300 Kelvin, moves the piston by 17 centimeter against the external pressure of 2 atmosphere. The cross-sectional area of the container is the work done by the gas is used. So this problem is regarding the work done by the expansion of a gas under constant external pressure. Okay, so so first we shall revise our fundamentals regarding the work done that is done by a gas under external pressure. So so if we know, if we have a for example, here we have a piston, and this is the pressure done either, and we have an external pressure that is PEX as shown here. Okay, so we have P external pressure here, and this gas is actually expanding from V initial. This is V initial and this is V final. So in order to determine the work done, what we have to do is we can plot as shown here pressure as a function of the volume. Now this is an initial volume, this is a final volume. Since the work done by the external pressure, work done by because of the expansion of the gas is equivalent to W, if we know it is equivalent to P multiplied by delta V. Since external pressure is constant, so whatsoever comes in the graph, the area of this graph will be given by the work done. Now this is possible when the external pressure remains constant. Okay, but for an isothermal expansion of a gas where the external pressure is actually changing, for that what we have to take is so we'll still take pressure as a function of volume plot, and we'll integrate this plot, and the area under this curve will determine our so for ideal gases we can determine this equation, that is minus nRT ln of V final minus V initial. Okay, now let us go to our problem back. The chemical reaction is taking place in a container. So the problem is the chemical reaction is placed in a container at 300 Kelvin, and it moves the piston by 17 centimeter. Okay, so against the external pressure of 2. So we have to determine the work done that is done by the expansion of the gas. Now okay, so we can do that. Okay, so this is our sample problem second. Okay, so now we have work done against. Now we know that work done against constant pressure, it is given by P external dV, where dV is a change in the volume. Now delta V is equivalent to V final minus V initial. Okay, now we have to determine how much is the volume change. Since we know that volume is equivalent to length, breadth into height, so volume is equivalent to cross section multiplied by the displacement. Okay, now from the problem, it is given that the cross section is 232 centimeter square and the displacement is done 17 centimeter. Okay, so the total volume change okay, so the total volume change will be, we'll multiply this up and it will be 39.44 10 to the power minus 14 meter cube. So this is the volume change that is done by the expansion of the gas. Now the total work done will be equivalent to P external multiplied by delta V. Okay, so the external pressure is given as 2 atmosphere and the volume change we have calculated as 39.44 10 to the power minus 4 meter cube. Okay, we also know that 1 atmosphere is equivalent to 101,325 pascals. Okay, or in other words 101,325 Newton per meter square, because 1 pascal is equivalent to 1 Newton per meter square. Okay, so putting these values we can calculate that the work done by by this gas will be equivalent to 799.2 joules or 799.2 Newton meter, because 1 joule is equivalent to 1 Newton meter. Okay, so that is our second problem. So that was the answer. Okay, so let's move to the next question which we have. Okay, now here is actually this is regarding the kinetic theory of the gases. Okay, so the question states that which among the following will be true for comparison of most probable velocity of the nitrogen with that of the neon. And so we have to determine the most probable velocity of nitrogen with that of the neon at 300 Kelvin. Okay, so in order to determine that, we'll just revise a little bit about the kinetic theory of the gases. So this kinetic theory of the gases is actually the assumption is actually on 3 basic assumptions. Okay, the first assumption is that the gas consists of the molecules of mass m and which are moving have a random motion. Okay, that means the motion cannot be predicted. Okay, the size of the molecules is negligible. That means they are considered as point objects which doesn't have any dimensions. That means the diameters are very much smaller as compared to the distance traveled between the collisions. The molecule only interact briefly, infrequently, and in elastic collisions. So the kinetic theory of the gases considers the gases as pointless particles which are very far from each other and does not have any force of interaction applying on them, and they only will interact with each other once they undergo collision. Okay, so once they undergo collision, they will interact with each other, and all the collisions are elastic collisions. That means no energy is lost. Okay, the total kinetic energy of the molecule is preserved. Now using the postulates of the kinetic theory of the gases, we can determine that this equation, that is P V is equivalent to 1 by 3 N M C square, where C is the velocity of gas molecules. Okay, velocity of gas molecules. M is the molar mass and n is the number of the particles. Okay, now from the kinetic theory of the gases, there are three main types of the velocities. Okay, so we have root mean square velocity, we have average velocity, and we have most probable velocity. Now first I'll see that okay, probably, yeah. So what will happen that once according to the kinetic theory of the gases, that what will happen once there will be an increase in the temperature. Okay, so if we see this is the function of relative motion of the molecule, and this is at low temperature. So once there is a low temperature, we don't have, and this is the molecular speeds. Okay, now at low temperature what we have is the molecular speeds are very low, or there are almost negligible amount of the molecule with higher frequency, with higher molecular speeds. But once we go on increasing the temperature, what will happen is the average number of the molecules with higher speeds are increasing. As a result, once we go on higher speeds, the average molecular energy or molecular velocity increases. Now on the basis of this kinetic theory of the gases, we are also able to explain by collision theory of molecular reactions how once we increase the temperature of any chemical reaction by 10 degrees, how the reaction rate is almost doubled. It's because the molecules or the reactants which need enough energy to react, the proportion of those reactants having enough energy to react actually increases by double. Okay, so this is the kinetic theory of the gas. Now from the kinetic theory of the gases, we have three types of the velocities. If we so the form of the molecules at temperature T is now if we see the Maxwell's equation. Okay, so it actually tells us the frequency, the number of molecules which have velocity in between v and dv. Okay, so this is the Maxwell's equation. Okay, so in this equation, if we plot this, so this is the function plotted as a function of the velocity. Now if we see this hump, okay, this function, there are three types of the velocity. One is most probable velocity, the average velocity, and okay, so we have is okay, so I have explained little bit about kinetic theory of gases. Okay, now there are three types of the velocities. One is called as the most probable velocities, second is the average velocity, and third is the root mean square velocity. Okay, so the most probable, if we plot the Maxwell's function as a function of the velocity, f as a function of v as a function of the velocity, we'll see a curve like this. Okay, so most probable velocity is the velocity that majority or the maximum number of the gas molecules have. So it comes at the peak. Okay, the most probable velocities is given by, so I will write most probable as VMP. It is given by 2 RT by M, where R is the gas constant, M is the molecular mass. Okay, so this is the most probable velocity. Similarly, then as I have shown in this, we have, this is the most probable velocity, we have root mean square velocity, and we have average velocity. So we have three types of the velocities that we can do. Okay, so here the question is regarding the root mean square. The question is regarding the mean most probable velocities. Okay, so we'll try to solve it as it is actually shown here. So this is the most probable velocity, that 2 RT by M. Okay, so most probable velocity of the nitrogen will be 2 RT divided by 28. 28 is the molecular mass of the nitrogen. Similarly for neon it is 2. Okay, so if we divide this by 2, we can calculate the ratio, and it comes out to be 0.852. So that means the most probable velocity of the nitrogen is 0.845 times to that of the most probable velocity of the neon. Okay, now we have another question. The value of critical constants of a gas are Pc is equivalent to 53.70 atmosphere. Critical velocity is equivalent to 71 centimeter cube per mole, and critical temperature is 291. The radius of gas molecules will be okay. So the question is regarding the critical constants of the gas. Okay, so we will a little bit revise it. Now you see these are isotherms of a gas. Okay, as we have seen here. Most probably these isotherms closely resemble that of the carbon dioxide. So if we see, so isotherm is the curve where the temperature remains the constant, as we see here. Now you see this curve, this corresponds to the 50 degree Celsius. Okay, so similarly we go on decreasing the temperature. Now if we see outside this hole is gas. Okay, this area, this inside is actually liquid. Okay, now there is, now if we talk about this point, so this point, it corresponds to a particular temperature. Now this temperature is called as a critical temperature. For example, for this gas it is 73 degrees Celsius. So the critical temperature is the temperature at which gas changes into liquid. Okay, so here the gas changed into liquid. Similarly here, this, if these conditions are met, that means at this pressure and at this temperature, we can convert a particular gas into the liquid. Okay, so this temperature, if we see from this, that if we increase the temperature above this, okay, if we increase the temperature, that means little bit higher. Okay, so what we will see is that no matter how much we increase the pressure, so no matter how much we increase the pressure or decrease the volume, we will not have any liquefaction of the gas. So critical temperature is the temperature above which a gas cannot be liquefied at all. Okay, now this critical now if we have a gas at a critical temperature and the volume that's occupied by the gas at that critical temperature and at critical pressure is called as a critical volume, and the pressure is the pressure that is required to liquefy the gas at critical temperature. Okay, now as I have written here, that they play a very essential role in the change of states. Now critical constants are critical pressure, as I have explained, critical volume, and the critical temperature. So this is called as a critical temperature. Okay, okay, now if we see that first we have the van der Waals equation of gases. So the van der Waals equation of gas, no, we have first we have the ideal gas equation. So the ideal gas equation is PV is equivalent to nRT. Okay, now we'll go to the van der Waals equation of the gases. Okay, now for van der Waals, he actually made some of the changes to the ideal gas equation so that it will explain some of the properties of the real gases. Okay, so one of the okay, so there were actually two main faulty assumptions in ideal gas equation. One was the force is almost that is acting is almost negligible, okay, on the particles, and the second is that the gases does not occupy any volume. So he made changes by introducing these two terms, and by introducing these two terms NB and NV, it's equivalent to R. This is called as a van der Waals equation of the state. Okay, so it is actually a triple root. It has if we plot this van der Waals equation of the state, it will be like this. Okay, So it has it's a triple, it has three values at a particular pressure. Okay, now if we see this is the van der Waals equation of the state. Okay, now if we have taken the van der Waals equation of the state, and what we have done is we have shown a, now in van der Waals or in any equation we will have an inflection point. Inflection point is a point in a curve where on one side there is a concave and on another side there is convex. Okay, so this is the inflection point. Now at the inflection point we will have both first derivative as well as second derivative 0. Okay, so what we'll do is we'll just take the do the rearrangements and do the first derivative of this, so we will get this value. Okay, and then from this van der Waals equation of the states we'll know that critical constant, critical volume will be equivalent to 3 times the van der Waals constant B. Critical temperature is equivalent to 8A by 27 RB, where R is called as ideal gas constant, and the critical pressure will be given by A by 27 B square. Okay, so we have to determine the question is critical constants are given, we have to determine the radius of the gas. Now how we'll determine is so we have a sample problem. Okay, now the critical constants are given in the equation, but we have to determine the volume of the gas. Now we know that critical volume will be equivalent to 3 times B. Okay, now there they have given is that critical volume is given is 271 centimeter cube per mole. Okay, that means 3B is equivalent to 271 centimeter cube per mole. Okay, so B will be given by 271 divided by 3 per centimeter cube per mole. Now also we know that B is actually related to the volume of the gas, that is the actual volume that is occupied by the gas particles. So it will be equivalent to 4 multiplied by 4 by 3 pi R cube multiplied by Avogadro's number. Okay, so this we can get from the van der Waals equation. Okay, now we know B, it is 271 by 3, then 4 multiplied by 4 by 3, 3.14 radius cube multiplied by 6.023 into 10 to the power 23 per mole. So from that equation we can get R cube as, if we compute this, we will get 8.96 multiplied by 10 to the power minus 14 centimeter cube. Therefore R, or the radius of the gas, will be 8.96 okay, so the cube root we will get 2.07 angstroms. Now this solves our problem. So we have determined the radius of the gas particles from the critical constants by relating it to the van der Waals equation of the states. Okay, that I have also shown here. Okay, now the another question that we have is, I think that was the, okay, from that assignment, that was the last question. Okay, now we have a second assignment. The second assignment is regarding the molecular interactions. Okay, yeah, so we have this. Okay, for an organic compound, the polarizability volume is 2.37 in 10 to the power minus 2 meter per cube, and the moment is 3.22 into 10 to the power minus 12 per centimeter. Calculate the relative permeability if the density of the compound and the molar mass is 170 gram per Kelvin. So polarizability volume is given, and it is dipole moment is given. We have to determine the relative permeability at 300 Kelvin. Okay, so for that we'll first I will give a brief introduction about the polarizability. Excuse me. You see, what is a polarizability? Now, if for example we'll take any atom or any molecule inside two parallel plates, okay, and now it will retain its shape. Okay, so as a result nothing will happen to its electronic structure. But if we apply a potential or an electric field across these two plates, so what will happen is that if this is negatively charged, right, so any atom or any molecule, it will have both electrons and it will have both proton nuclei. The electrons will get dragged towards the positively charged, as is shown here. You see here, whereas the nuclei will get dragged towards the, because the opposite charges attract. Okay, similarly this can be done if we take another charged particle. For example, we have a particle that is here, that's completely uncharged. So what we'll take is, we'll take a sodium, any metal ion, for positively charged. So what will happen is that the electron cloud will get dragged towards this. If we take a positively charged particle like HCl, this will get dragged towards this. So this tendency of the molecules to generate a dipole within them when they are subjected to the external electrical field is called as polarizability. Okay, now polarizability plays a very important role in intermolecular interactions. Okay, so it is because of the polarizability that we see that there are dipole induced dipole interactions, or induced dipole interactions, or London forces or dispersion forces. They occur because a particular ion or a charged particle is able to create or generate polarization on another charged particle. Now because of that polarization, what will happen is that they will attract, okay, or they will repel according to what the particles are, what charges are generated. Now as I have shown here, okay, now okay, this polarizability is actually this, for example, if we take a material or any substance that is for example circular, now polarizability can be isotropic or it can be anisotropic. That means the amount of polarization on this side or on other side can be different, or it can be same. Now if it is same, then the dipole moment, induced dipole moment that is generated is directly proportional to the applied electrical field. Okay, directly proportional. So that means P is equivalent to alpha E, where this alpha is a constant of proportionality, and it is called as a polarizability constant. Okay, this alpha is called as a polarizability constant. P is the induced dipole moment, and E is the electrical field that produces the dipole moment. Okay, so the this polarizability has an SI unit of coulomb per meter square per volume. Okay, so now, or we can use in different CGI units. Now this polarizability is in SI units. If we want to convert the polarizability, this is polarizability, in CGS unit, that time it is called as polarizability volume. Okay, the only difference between polarizability and polarizability volume, alpha and alpha star, is that alpha is in SI units and alpha dash is in CGS units. Okay, so if we want to convert this into CGS unit, what we have to do is, this is expressed in terms of centimeter cube. Okay, the polarizability volume. So alpha dash, that means the polarizability volume, is equivalent 10 to the power 6 divided by 4 by epsilon naught. It is epsilon naught is permeability of free space. Then we have force dot meter square. Okay, so in other words, we can write that that alpha, that means the polarizability, is given by 4 pi epsilon 0 divided by polarizability volume, or polarizability volume is given by 4 pi epsilon 0 divided by alpha. Okay, so this is the polarizability volume. Okay, now polarizability volume depends upon the electrical susceptibility. Okay, as I will show you later by Clausius-Mossotti relation. For example, so Clausius-Mossotti relation is this 4 pi, where R is called as a molar reflectivity. So molar reflectivity is given by 4 pi by 3. Na is Avogadro's number, and alpha c is called as electronic polarizability. M is the molar mass, P is the dipole moment that is induced, whereas ER is dielectric constant or the relative permeability. Now this I will show later. Okay, now this polarizability, as I told you, this can be isotropic, or a particular material can be an isotropic with respect to polarization. That means the polarizability induced is different across different directions. Okay, so for example, I have shown here. So then at that time the polarizability is denoted in the as a tensor quantity. Okay, so this is for example the tensor quantity. If we see the diagonal elements, they determine the when the electrical field has been applied across x direction, how much potential or how much dipole moment has been generated across x direction. Now if we take polarizability component alpha zx, so it tells us that how much polarizability has been generated across x direction when the electrical field was applied across z direction. Okay, so this is called as a polarizability vector. Now this polarizability can be related to a number of properties of the system. Okay, the first property is relative permeability or dielectric constant. Now this dielectric constant or relative permeability, it tells us that when we put two dipoles or two electronic charges we put inside a medium, they attract each other. Okay, now if we put the same particles inside the vacuum, their attraction or their repulsion, it will increase. So in any particular medium, the attraction, the force of attraction or the force of repulsion between two charged particles, it decreases. Now that is called as a relative permeability. It tells us how the coulombic forces between two charges of a material, or 2 point charges of a material, are affected in a particular medium with respect to that of the vacuum. Okay, so relative permeability is, or also called as a dielectric constant, is given by this quantity sigma r is equal to sigma divided by sigma naught, where sigma is the permeability in a particular medium, and this is permeability in vacuum. Okay, for example, we know that permeability of relative permeability of water is 80. So that means once we put 2 point charges inside water, okay, the force between them is decreased by 80 times as compared to if the same particles are put inside the vacuum. Okay, so we also know that relative permeability is related to the electrical susceptibility by relative permeability 1 plus xc, where x is called as a relative permeability. Okay, so in practice, in order to determine the relative permeability, what we are doing is that we are creating a parallel plate capacitor. Okay, and then we are filling up the medium in between the parallel plate capacitor with the material in which we want to determine the relative permeability, and then we determine the capacitance. Okay, then this medium is removed and the capacitance is again determined. This ratio tells us about the relative permeability. Okay, now we have seen here electrical susceptibility. Now we'll explain a little bit electrical susceptibility. Electrical susceptibility is actually a dimensionless constant. It tells us the degree of polarization of any material with respect to applied electrical field. Okay, for example, if we use an electrical field E on any material, and the polarization density, that means the number of dipoles created per unit volume, okay, it's called as polarization density, is given by P. So this P is directly proportional to E. Now here P is given by epsilon 0 xe and E. This xe is called as an electrical susceptibility. Okay, so polarization density is related to the applied electrical field by electric susceptibility and relative permeability. Okay, now we have another parameter regarding polarizability, that is molecular polarizability. Okay, so it actually relates the individual the dipole moment that is created on individual molecules. Okay, the dipole moment that is created on individual molecules to that of the electrical field that induces that dipole. Okay, so for example, this is the molecular moment, this is the dipole moment that is created on a single molecule, and it is directly proportional to the electrical field, local electrical field. Okay, so this alpha is called as a molecular polarizability. Okay, okay, molecular polarizability. Now but what will happen is that if you have a material that consists of the majority and a lot of molecules, every individual molecule will have a different electrical field or local electrical field. If we consider that individual local electrical field is same as compared to that of the bulk electrical field, then what we can do is we have this equation alpha epsilon 0 alpha E local, right? Then what we can put is we can put this equivalent to that of this equation, okay, per unit volume. Okay, so this is number of the molecules per unit volume. So equating this molecular polarizability with electrical susceptibility, we can determine that xe is equal to n times alpha, but this is only possible when the field is consistent in the medium throughout. Okay, if the field is not consistent, then we have to use the Clausius-Mossotti equation that tells us that molecular susceptibility, that means xe by 3 times xe is equivalent to n alpha is called molecular polarizability divided by 3. Okay, so now we'll go about the Clausius molecular polarizability. There is a lag. Okay, so we'll show about the Clausius-Mossotti equation. Okay, so this Clausius-Mossotti equation, it expresses Clausius-Mossotti equation, it expresses the relation between the dielectric constant, that is xe, and the molecular polarizability. Okay, that means molecular polarizability or alpha. Okay, now This is the Clausius-Mosotty equation, in which this epsilon r is relative permeability, n is number of molecules per unit volume of any material, and alpha is called as a molecular polarizability. Now in case that the material is consisting of different species, then what we have to do is we have to add up the molecular polarizability of all the right hand sides. So this equation is given. This is called as a Clausius-Mosotty equation. Now similar to it, there is an another equation called as Lorentz equation. So it is similar to that of the Clausius-Mosotty equation, and it actually relates the refractive index rather than uh, uh, permeability. So the refractive index of a dielectric constant of a okay. So if we the Lorentz equation in CGS units is given by n square minus 1, where n square is called the refractive index, 4 pi n alpha m, where n is called the refractive index, n is the number of molecules per unit volume, alpha is the mean polarizability, and this is valid for which are homogeneous liquids or homogeneous gases. Okay, but if we see that majority of the gases, their reflective index is near to 1, so n square is 1, so this equation we can reduce to n square minus 1 is equal to 4 pi, or simply we can write n minus 1 is equal to 2 pi n alpha m. Okay, now there is another type of n. Now see, if we take a take any substance or inside a material, now there can be two types of the polarizations. Okay, one is induced polarization. So induced polarization occurs when the electronic clouds is distorted from that of the, so this is positive and this is the distortion of the electronic cloud. Okay, and when the electrical cloud is distorted because of the applied field, but there can be the orientation polarization only if a particular molecule or a particular substance contains the dipole. So what will happen is that once we use the electrical field, these dipoles will orient themselves along the dipoles. As a result, that's called as an orientation dipole moment. Now Debye calculated the orientation polarization to be equivalent to mu square divided by 3kT, where mu square is called as dipole of the individual molecule. So total dipole that is induced in any system will be equivalent to alpha will be equivalent to, this is polarizability is given by induced polarization plus orientation polarization, that is given by alpha 0. So alpha will be equivalent to alpha I plus mu square divided by 3kT. Okay, so while solving the equation we have to use these two. Okay, now we'll go back to the question that we had is we have a polarizatory volume and we have to and the dipole moment, and we have to calculate the molar mass. Okay, so what we'll do is we'll okay okay so we'll see what is given. Okay, so it is 3, we have now okay, now what we'll do is we'll use the equations that we have used here, that means relative permeability, electrical susceptibility, and Clausius-Mosotty equation, in order to derive the answer for this equation. So for that what we'll do is we'll see what are the given things. Okay, so what we have been given is the mu has been given as 3.22 into 10 to the power minus 29 coulomb meter. So dipole moment is given, then polarizability is given. Okay, now we know that polarizability volume that actually I have showed is given by polarizability divided by 4 pi epsilon 0. Now as I told that polarizability volume is the polarizability in CGS units. Okay, so this is in SI units, so this is in CGS units, so it is given by this. Okay, so from this, and we know that epsilon 0, that is permeability of the free spaces, 8.85 10 to the power minus 12 coulomb square per Newton per meter square. Okay, now we can determine alpha from this equation, 4 pi epsilon 0 epsilon dash. Epsilon dash is given, so 4 multiplied by okay, so we have got this equation. Now if we calculate, it will come 2.634 into 10 to the power minus 31 per joule coulomb square meter square. Now we also know that 1 joule is equivalent to 1 Newton meter. Okay, so now we'll use the Clausius-Moissault equation that I have showed before. Okay, Clausius-Moissault equation that relates the dielectric constant okay, so this is the Clausius-Moissault equation. This relates the dielectric constant to that of the permittivity. Okay, now we know that total permittivity, that is will be given by alpha will be equivalent to Na by 3EC alpha plus mu square divided by 3kT. See, this is the induced polarization and polarizability, and this is the orientation polarizability. Okay, so we have to include both in here. Okay, so that means from this equation we can determine alpha as 6.023 multiplied by 10 to the power 23 per mole divided by 3 multiplied by 18.85 into 10 to the power minus 12 per joule coulomb square per meter. Okay, so if we solve this equation numericals, we will get 5.94 into 10 to the power 3 meter cube per mole. Okay, now we have determined the alpha. Okay, now we'll go to our previous equation, that is Clausius-Moissault equation, which tells us the relation between polarizability and the dielectric constant. Okay, so sigma r minus 1 divided by sigma r minus 2 will be equivalent to, we know the value of Pm. Okay, so alpha we actually determined, it was 5.94 into 10 to the power 3 meter cube per mole divided by m is the molar mass, then okay, so that means epsilon r minus 1 will be equivalent to, if we calculate this, it will come 4.62 into 10 to the power 7 epsilon r minus 9.24 into 10 to the power 7. So epsilon r will be almost equivalent to 9.42 into 10 to the power 7 divided by 4.62 into 10 to the power 7 is equivalent to 2. Now this relation, as I have shown previously, that these relations are, for example, this is the relation where this one, okay, n determines the number density, alpha determines alpha is the polarizability, okay. So we needed to know the number density, okay. So that concludes our first question. So we have determined that dielectric constant is almost equivalent to that of the 2. So here the density of the compound was given, that I have actually used here. So the answer is 2. Okay, now we'll go to the second one. How much energy is required to break hydrogen bond in 1 mole of water molecules, assuming that the partial energy, okay. So this is regarding the intermolecular interaction. We have to determine the energy of 1 mole of the hydrogen bonds inside the 1 mole molecules, okay. So the partial charge and the length is determined. So how we'll determine this is, will determine the potential energy of the hydrogen bonds inside 1 mole, and negative of that energy will be given by the energy that we need in order to break those many bonds that are present in 1 mole of the hydrogen of the water molecules, okay. So we know the what is given, okay. So the given is what is given. So given is the charge that is present on the hydrogen, that is 0.42 atomic unit, and then we have the charge on an oxygen atom, okay, that is given by -2 into 0.42, that is minus 0.84, okay. Now since we know that the energy or the potential energy of two hydrogen potential energy of the bond will be given by this is the potential energy. So we'll put QH minus 0.42 multiplied by 0.84 divided by 4 pi this epsilon r into epsilon 0. So this is okay. Then we have r, that means the distance between hydrogen and this. So that is given by 190 into 10 to the power minus 12 meter, okay. So we know that dielectric constant for the water is 80, so we'll put that value. So we know that here I have used actually E, electrical charge 1.6 into 10 to the power minus 19 coulomb, because we need to get this equation in SI units. Okay, then we have 4 3.14. okay, then multiplied by 8.85 into 10 to the power minus 12 per joule coulomb square meter inverse into 190 into 10 to the power minus 12 meter. Okay, then multiplied by dielectric constant 80. Okay, so that means the potential energy used to break, it will be equivalent to 5.34 into 10 to the power minus 21 joules. Okay, now this is the energy that is required to break one molecule. Okay, but here we have to break uh, 1 mole. So for 1 mole we have to multiply it by Avogadro's number, right? Avogadro's number is 6.023 10 to the power 23 per mole into minus 5.34 into 10 to the power minus 21 joules. So total will be minus 3.22 kilojoule per mole. Okay, so this will be the right answer. Okay, now we'll go to the next problem. Which of the following have the least dipole moment? Okay, so these are these molecules that are given, and we have to check that which one has the least dipole moment. Now in order to have the idea of the dipole moment inside a molecular structure, we need to know the structure of the molecule. Okay, so without that structure we will not be able to come, because dipole moment is an dipole moment is a vector quantity. So for example, if I'll write, okay, so if I have a positive charge and I have a negative charge, so this is positive and this is negative, and if they are connected, okay, so this will be this is a dipole. Okay, so the charge on this is Q, charge on this is Q plus, this is Q minus, and the distance between them is H. So the dipole moment will be given by Q into H. So this dipole moment has it is actually directed from a positive to the negative charge. Okay, now if we have multiple dipole moments, so as I told, that dipole moment is a vector quantity. So if for example we have a dipole moment along this equivalent to mu1, and we have a dipole moment along this equivalent to mu2, if we add them up vectorically, we will determine that mu-t is given by mu1 plus mu2 vector quantity, it will be 0. Okay, so similarly we are trying to solve here. For that we need to know what is the structure of these molecules. Okay, so the first molecule that we have been given is CHCl3. Now all of you know that the structure is pyramidal, sorry, tetragonal. Okay, so this is Cl, this is Cl, this is Cl, and this is H. Okay, the second molecule we have been given is NH3. So this is N, this is H, and we have 2 electrons. Okay, the third molecule is CH2Cl3. CH2Cl2. Okay, chlorine, H. The last one is CHCF3. Now we see that we have to consider the electronegativity. Okay, so electronegativity. Now we know that electronegativity of fluorine is higher than chlorine, then carbon, and then hydrogen. So that means that if we make a the more electronegative atoms, they will drag the electrons towards them. As a result, you will have a negative charge, and on the other you will have a positive charge. Okay, so now if we write here if we say the dielectric constant, it will be directed towards here, so directed towards here, directed towards here, so we will get a net dielectric constant towards the middle axis like this. Okay, this is a net dielectric constant. Here what we'll have is these hydrogens will be positive charges, so the net dielectric constant will be towards the top little bit. Okay, similarly for the carbon and this hydrogen, this will be towards here, this will be towards there, and so the net dielectric constant will be the sum of these two. Okay, so that will be actually the sum of these four, so this will be this and this will be this. Okay, similarly the dielectric constant for these bonds will be like this. Okay, now we know that fluorine has the maximum drag, so and all the three bonds are towards one, so as a result the dielectric constant for CFCl3 is actually maximum. CF3 is actually maximum. Okay, and to be precise, it is almost 1.65 dBi. Okay, then we have Cl here, we have two Cl's against each other, and the other, then we have CH2Cl2, it has 1.6 dBi. Okay, then we have NH3, it has 1.46 dBi. Then we have CHCl3, it has 1.03 dBi. So that is our answer. Okay, so the maximum is CH3 CF3 we can determine. So this is the okay, least dipole moment is CHCl3, so CHCl3 is the right answer. Okay, next we have question. It is regarding the molar mass is given 106 grams per mole and the density is given. We have to determine the polarizability volume. Okay, polarizability volume is given and we have to determine the refractive index. So we have to use the Clausius-Mossotti equation that I have already showed. So now let us use first we'll write polarizability volume is given by polarizability divided by 4 pi epsilon naught, and that means alpha is equivalent to polarizability volume multiplied by 4 pi epsilon 0. Okay, so this is our now we'll determine the polarizability from the polarizability volume. Now it is 4 multiplied by 4.14. now polarizability volume is actually given, that is 8.85 10 to the power minus 12 per joule coulomb square per meter. This is the value of epsilon multiplied by the given quantity polarizability volume. Okay, from this we can determine So this we calculate. Now we also know from the Clausius-Mosotti equation. Okay, I'll write it again. The Clausius-Mosotti equation I actually explained before. We can see it again. Yeah, so this is the Clausius-Mosotti equation. Epsilon minus 1 divided by epsilon 2 plus 1 is equivalent to n alpha divided by 3 epsilon 0, where n is called number density of the molecules, number per cubic meter. Okay, so number per cubic meter. So this equation we'll use here. Okay, so Clausius-Mosotti equation we have. So what is the Clausius-Mosotti equation? It is epsilon r minus 1 divided by epsilon r plus 2 is given by p and a divided by 3 m epsilon 0 into alpha. We can call it rho, where rho is density of substance, Na is Avogadro's constant, m is molar mass. Okay, so technically we have to determine the number density. Okay, so we had to determine the number density n, because the Clausius-Mosotti equation there is number density. Now it is number of molecules per unit volume. Okay, per unit volume, it is number of molecules per unit volume. This is number of molecules, this is volume. Okay, so we have to determine this. Now since the quantity is density is rho is given by mass per unit volume. Okay, but we know that mass in unit volume will be given by molar mass multiplied by Avogadro's number for 1 mole of the gases. Okay, and for 1 mole of the gases it will be n will be given by Na multiplied by 1 mole of the gases, and V is the molar mass. Okay, so now we have to determine from the density we have to determine n by V. Now since yes, we can approach this another way. So we know that a density is mass by volume. Okay, so for if we take 1 mole of the gases, okay, so 1 mole of the gases, the dense number of the molecules in 1 mole of the gases will be given by Na, right? So Na, so what we have written is n number density is given by density Na by m, where m is called as molar mass. So okay, now we'll use this equation, and we derive it from this. Okay, so let us determine this quantity, that means rho Na alpha divided by 3 m epsilon naught. Okay, so the rho is given, that means the density is 9.3 kg per meter cube. 6.023 into 10 to the power 23 is n, and polarizability we have determined to be 30 or 3.45 into 10 to the power minus 10 per joule coulomb square meter square. Okay, divided by 3 multiplied by, it is molar mass 106 gram per mole, permittivity of the free space 8.85 into 10 to the power minus 12 per joule coulomb square per meter 1. Okay, so if we compute this, we'll determine 6.67 10 to the power minus 2. Okay, now we know that from Clausius-Mossotti equation that rho Na alpha divided by 3 m epsilon 0 is equivalent to epsilon r minus 1 divided by epsilon plus 2. So this is from this equation. Okay, so epsilon r is equivalent to 2 multiplied by 0.0667 plus 1 divided by 1 minus 0.0667. It will be given by 1.21. We know that refractive index NR is almost equivalent to, this is from here. Okay, so n square, if we consider that number density is very less, and then this multiplier, so n square will be equivalent to alpha m. Okay, number density, this is for gases, so if it is almost equivalent to this, we can determine n r is equivalent to this is our answer. Okay, now let us solve one more question. The question we have is, we have the electric field that is experienced by an anion when a molecule with a dipole moment of 0.3 approaches an anion, assuming the distance between the molecule and okay, so this question is about the question is about the induced dipole, induced dipole. Okay, so if we have a system that is like this, okay, so all this is negatively charged, and inside this is a positively charged species. Okay, then right now the dipole moment is 0, but once we put another dipole, for example we have a dipole here, okay, in which this is the positive charged and this area is negatively charged, right? This is negative, this is positive. So what will happen is this positive charge will attract these electrons towards itself, okay, and this will go away from each other. So as a result, after some time what we will have is some sort of a charge distortion. So it will be like this positive charge will go around here, okay, and majority of this will be negatively charged. So as a result, a dipole has been created here, okay, momentarily dipole, and this dipole is now how much okay, now how much charge that will be generated on this. For example, if this is a dipole is equivalent to P, right? P is the dipole that is induced at Pi. Now it will depend upon the distance between this and these two, okay. So the closer it will be, the more electric field it will have. As a result, more dipole will be generated, okay, because we already shown that the induced dipole is directly proportional to E, or in other words, P is equivalent to alpha E. That will depend upon the, now we have to determine that how much will be the electric field intensity, okay. For that we have to see that how much is the energy of interaction between a dipole and a point charge, okay. So in your secondary classes you might have the energy of the interaction is minus mu, where mu is the dipole moment, q is the charge, 4 pi epsilon r square, okay. So mu is given as 0.037 dBi, okay. We know that 1 dBi is equivalent to 3.35 into 10 to the power minus 30 coulomb meter. We also, this is given minus 1 point, okay, and the distance between them is given as 13 angstroms. We can convert that into SI unit, okay. So thus it will be given by minus 0.73 okay, multiplied by 0.73 multiplied by we'll have 3.335, that is the dipole that is given. Then we'll determine Q is 1 minus 1.6 into 10 to the power minus 19 coulomb. 4 pi is 3.14 multiplied by epsilon naught, it is given by 8.85 into 10 to the power minus 12. Yes, you can write in the chat or how directly. It's not audible. Oh, okay, sorry. Okay, so we are trying to solve the problem that is how much. Yeah, so this is the problem. We have to check the electrical field that is actually experienced by an ion, a point charge, when a molecule with dipole moment of this is approached, okay. So as I have explained before that if we have an anion and we have a dipole around it. So what will happen is we'll induce a charge on it, okay, because of the dipole interactions. So if this is positively charged, and it will attract the electrons towards it, or if it is negatively charged, it will repel the electrons. Now depending upon the distance between these two, we will have different electrical field will be experienced. As a result, different charge will be generated, okay. So we have to determine that electrical field is, now it's already written that how much electrical field has been generated. So we have to determine the distance is given, so we have to determine the charge. So from this I have approached the problem in which the potential, the energy of the interaction is minus mu. Mu is the dipole moment, and q is the charge, 4 pi epsilon, and r square is the distance between these two, okay. So will this mu is given, okay, from this mu is given, q is given, and r square is given, so we can determine v, okay. So if we use this equation, we can determine v to be 2.037 into 10 to the power minus 21 joules, okay. So this is the anyways, I'll share all the document and in the group. If anyone has the query, this will be available on the YouTube also. So in the later, if anyone has a query regarding they are not able to understand anything, or they want some thing to be explained more, then we can take up in the next assignment. So for today, I'll be sharing the presentation, that is this presentation actually. So I have explained a little concept about the polarizability and different polarizability relations, like molecular polarizability, Clausius-Mossotti equation, electrical susceptibility, and how the polarizability depends upon polarizability tensors, then relative permeability, permittivity, electrical susceptibility, and molecular polarizability, okay. So using these equations, Clausius-Mossotti equation and Lorentz equation. So using these equations, I have tried to solve some of the problems in the previous year's assignments, okay. So these problems will be available, they'll be both the answers as well as this presentation. It will be available in the NPTEL link somewhere, okay. So if you have, anyone has any question or anything that they are not able to grasp, then they can tell in the next session, okay. Thank you for today. We'll meet in next session. Thank you.